Okay, let's go ahead and get started. We have covered most of the main ideas that will be on that next exam. And for the rest of the time before that exam, I'm just going to be working problems to show you how to use those ideas and help you get, I hope, more comfortable with those ideas. As I mentioned before, these problems very quickly turn into algebra problems. And what we see over and over again is that we have a double hump distribution on the exam, where those who feel comfortable with algebra do better, and those who don't enjoy algebra really struggle on this next exam. Before we get started today, is someone willing to give us an opening prayer?
Our dear Heavenly Father, we thank you for this day and for the opportunity we have to be here at BYU to gain an education and to become more like thee. We learn more about this earth that thou hast created. Father, we pray that the Spirit might be with us, that we might be able to learn and understand these concepts and be prepared for the next exam that we have. Father, we're grateful for the preparations of Dr. Francis, and please bless him with a clear mind and spirit as he teaches today. Father, we love thee and we're grateful for thy Son, and we leave thee this prayer humbly in the name of Jesus Christ. Amen.
Okay. We last day we talked about the three different flavors of collision, and what we found was that we divided them up depending on how much energy, mechanical energy, was lost or not lost during that collision. If none of the mechanical energy was lost, we called that elastic. And we found that that word elastic means a whole lot different than in physics than it does in everyday life, what you would expect at Staples when you bought elastic bands. If you lose some of that mechanical energy, we call it inelastic. And in the special case where the bumpers stick together, lock together, and it becomes one ugly Volvo with 8 wheels, we call it maximally inelastic because it loses the most mechanical energy allowed by law. By what law? By Newton's third law. By Newton's third law. Now, we had this demo where we dropped a rubber ball on a rubber mat and a steel ball on a steel mat and a glass ball on a glass mat, and it was kind of small and unconvincing. So I've brought well, actually, let's remind ourselves what the answer was. With your clicker, let me get you started. Now you can vote. And we all know the answer, so if ever there was a time that we should get this 100% right, now's the time. Oh. Okay, get your vote in. Last call. Okay, it was glass on glass. And so here's an old demonstration from years ago. Okay, here's the happy ball. Here's the glass on glass. That's the most glass. Okay, and remember, the glass on glass was the most elastic because the glass did not deform, because we didn't use any of the energy to change the shape of the glass marble or the glass plate. Yes,
So then I would assume,
coming up there in just a second.
I would assume that steel is a lot less, like, it doesn't mold and it doesn't change form than rubber. So why did steel have like?
Well, Brinley, that's a very good question. And I wish that I had brought those plates along with me. And that metal plate there, you would see was just pitted from me doing this demo over and over again. So it wasn't really a super hard steel plate. You've got different types of steel, some that are a little bit more malleable than others. That's an excellent question. Thank you. Okay, let's look at this example where instead of two cars coming towards each other, we have one car that's just parked and the other car's coming in at 30 meters per second. And we're told that the bumpers lock. And so the question is, right after that collision, and I mean right after, I don't mean 2 minutes after, I mean right after, how fast do they have to be going? Tell your neighbor real quick. Okay. I hope everyone told their neighbor 15 meters per second. We found last day that in a collision, momentum has to be conserved for the system of everything that collides. Well, I just doubled the amount of mass that was moving. And so that means to keep the momentum the same, I have to cut the velocity in half. So it would be 15 meters per second. Is the kinetic energy after the collision zero? No or heck no? Heck no. So tell me what flavor of collision this is. Is it elastic, inelastic, or maximally inelastic?
I was thinking about. Okay, I was thinking about a roll.
No, you really don't want to. Like, we're a mouse, probably studying for the first like, just go, click, and this should be like.
Okay,
An hour and you.
it's not rocket science. Oh, wait, it is. That's what we're studying right now is rocket science. Yes. Rocket science is built upon the conservation of momentum, which of course is built on Newton's third law. Okay, last call. Oh, we're all over the map. We are all over the map. Okay, the answer, of course, is maximally inelastic. And I asked this question to make a point, and that is the definition of maximally inelastic is the bumpers lock. Full stop. That's it. Okay. We don't have to lose all of the mechanical energy. In this collision, we lost the most amount, the highest amount of mechanical energy allowed by law. Third law. Okay. It is not possible for these two to collide and be stopped. That would violate Newton's third law. The universe would stop existing, cats and dogs living together. It'd be awful. Okay. As long as the bumpers lock, we lose the maximum amount of mechanical energy. Now, this is a problem from your homework, and it's an old exam question. And we put it on the very front of the exam, first question, because it was super, super easy, and we wanted everyone to get something right. A boxcar traveling at 10 meters per second approaches a string of 4 identical boxcars sitting stationary on the track. The moving boxcar collides and links with the stationary cars and the five move off together. What kind of collision is it? Maximally inelastic, okay? The five move off together. What is the final speed of the five cars immediately after the collision? You may take the mass of each boxcar to be 18,537 kilograms. Now, when my friend Jeff Adams and I were team teaching in 98, we put this question on the exam and I said to Jeff, we're going to get asked all night long what the mass of those cars are. We didn't have that last sentence in there. And I said, we should tell them that it doesn't matter as long as they're all the same. And Jeff got an evil grin on his face and he said, I've got a better idea. Let's give it to them. And he pulled that number, 18,537 out of his left ear. I watched him do it. Okay. And it was amazing as we were grading that exam late into the night, everyone in the class punched that number in over and over and over again when they didn't have to. So let me show you how we're supposed to do this problem. Visually, this is what it looks like. The one car comes in at 10 meters per second. It links, and the mass of a car is 18,537 kilograms. Okay. It links together and they all move off at some final velocity. Well, again, this is a collision, and so we conserve momentum. The equal sign is the collision. Everything to the left of the equal sign is the initial momentum. That's the momentum of the one car, and this is the momentum of the four cars. And you see that I've wasted blue photons, okay? Because we don't need that. And then after the collision, all five of them are moving together at some final velocity. Well, the equation now looks like that, and I don't care what the mass of a single car is because it cancels out. What's important is that they are the same, each and every one of those cars. See if your neighbor is on the bus. So the final answer is 2 meters per second. Are there questions on that? Now, when you get to that next exam, every question is going to be about energy or momentum. And your most important decision at each question is, which is it? Because if you try to solve an energy problem with momentum, you got zero chance of getting it right. If you try to choose a momentum problem with energy, you have zero chance of getting it right. And so you've got to make that distinction right at the beginning. Now, it's not that the equations stop being valid. I mean, in this problem of the collision, the Verk energy equation is true, okay? It's just that we don't know how to use it. We have all these messy buckets like the energy of deformation, the heat energy, the energy is conserved, but it goes into buckets that we don't have equations for. Not just we in this class, but we as human beings. The energy of deformation for a Volvo is just way beyond us. Okay. And so even though Verk energy is true, it's not useful. Now, wait a minute, Greg. Energy is conserved, the type that we had formulas for in this type of collision. Well, yes, it is. But remember that elastic collision happens once every blue moon. And you don't know when you start a problem whether it's a blue moon out. Okay? You can't assume that this is going to be conserved because it rarely is. And you never know when you start the problem whether it is in this particular case. Likewise, when we're dealing with a Tarzan swing and we're trying to find the velocity at the bottom of the swing, that looks a whole lot like the bowling ball of death. And we found that we could easily solve that problem with energy. I have potential energy here. I have kinetic energy here. The Tarzan swing does no Verric because it's pulling along the vine and Tarzan's moving perpendicular to the vine. So that does no Verric. Now, could we use momentum to solve this problem? Well, yes. If you're really, really good at vector calculus. Because remember, what changes momentum is impulse, force times time. And impulse is a vector in the direction of the force. And the force exerted by the vine on Tarzan is changing direction as he swings down and also changing magnitude. So we could use the impulse momentum theorem, but only if we're really, really good at vector calculus. And that's what we typically call calculus 3. And people, that's not what you want to be doing in the middle of an exam. Okay, I wouldn't solve it this way. You might. Okay, so how do I know which problems are energy and which problems are momentum? Well, let me suggest this decision tree. The first question you ask yourself at the beginning of every problem is this a collision? If it's a collision, we know that momentum is conserved. Well, we got 3 flavors of collision: elastic, inelastic, and maximally inelastic. For which of those flavors is momentum conserved? All of them. Every single collision is a conservation of momentum problem. And so you can go right there. And remember, the initial means right before the collision, and the final means right after the collision. Okay? Now, if it's not a collision, ask yourself, is time involved? Am I given time? Am I asked to find the time? If so, it's still a momentum problem, just not a conservation of momentum problem. The momentum in the morning is equal to the momentum at night, except when I have an impulse of force times the time acting on the object. Okay? Now, if time is not involved, that's an energy problem. And you use the standard Verric energy theorem, the energy in the morning is equal to the energy at night, except when I have external Verric done on the system. Check that your neighbor understands what that decision tree is saying there. Yes.
I know that the MDP.
The equations on the exam are exactly the same as are on the sample exams that I posted. And so if you look on there, you'll see that those momentum equations are there.
Rather actually have.
I don't think any.
Folks, remember, it's a multiple choice exam. And you can be sure that when I'm working out what to put as distractors, I'm going to take an energy problem and try to solve it with momentum and get a bogus answer. Okay. So if you're working the problem with the wrong principles and you find your answer is one of the choices, don't do a happy dance. Okay. You be thinking about this decision tree at the start of every problem. Okay. Some collisions look exactly like explosion because they are. Okay. An explosion is a collision. A firecracker going off, like in the tutorial homework, is just the left side pushing on the right side and the right side pushing on the left side. That's a collision. Here's an example. An astronaut is motionless in outer space. Upon command, the propulsion unit strapped to his back ejects some gas with a velocity of 32 meters per second. And the astronaut recoils in the opposite direction with a velocity of negative 0.3 meters per second. After the gas is ejected, the mass of the astronaut is 160 kilograms. What is the mass of the ejected mass? Well, visually, it looks like this. He's out in deep outer space, just floating around, okay? He's got no velocity. There's no spring energy. There's no springs anywhere close. He's far from any planet, so there's no gravitational energy. His mechanical energy, the types we have formulas for, is zip. And then he pushes the button and he goes to the left, the gas goes to the right. But remember, energy is not a vector. I don't have energy to the right or energy to the left. I've just got energy. And so he's got kinetic energy. The gas has kinetic energy. Now we've got more mechanical energy than we had before. Energy is not conserved, okay? Energy is not conserved. But momentum is. Momentum is. And so if I look at the momentum before he pushes the button, that's zero. The momentum after he pushes the button, I can write like this. There's the momentum of the astronaut. There's the momentum of the gas. And again, because it's a vector, I have to choose a positive direction and a negative direction. And I've chosen the right is positive. When I conserve momentum and set the initial equal to the final, I get an equation that suddenly turns this into algebra. And when I solve for that mass of the gas, I get 1.5 kilograms. Okay? Check that your neighbor followed that example.
Yes.
Not.
Now, where did that kinetic energy come from? It seems like magic. I had no mechanical energy and now I've got some. Well, remember, mechanical energy is kinetic plus the potentials that we had formulas for, gravitational and spring. Well, there's also a potential energy called chemical potential energy. And that's the energy stored in that backpack, just waiting to be released by pushing the button. We don't have a formula for it, so it's not helpful in solving problems. Okay. Now, a little bit of market analysis here. When I say momentum is conserved during a collision, what am I saying? Am I saying total momentum for the system adds up to zero before and after the collision, or total momentum for the system stays the same before and after the collision? With your clicker, tell me what that means.
You're like, how much is going up every time? Sure.
Okay.
Wow.
Last call. Is that all of us? Good. The answer is, of course, B. Now, we've had a lot of examples where the momentum happens to be zero. But that's not what conservation means. Conservation just means it stays the same. If it started out zero, it stays zero. If it started out 12, it stays 12. It stays 12. Okay, now 3 or 4 times or 6 times on this next exam, you're going to need to solve what I call the basic collision problem. And this is what it looks like. You got 2 blocks, they're sliding together towards each other, and they collide. And after the collision, I give you one of the final velocities, but not the other. And I ask you, how fast is that blue block traveling? And is it traveling to the right or is it traveling to the left? And so if you tell your neighbor real quick how you would solve this problem.
Oh, and sad shoe.
I think that makes sense. Just like it's adding.
Yeah, 15.
I'm out of sense. See? Oh, well. Oh, yeah.
No,
How's that going? I wish I could.
Okay, because this is a collision, we would start right here. And because momentum is a vector, I will need a coordinate system. There has got to be a better. I have a plethora of them. Okay. Now, initially, before the collision, I have a 3 kilogram block moving at 5 meters per second. And it's moving in the positive x direction, so that's positive momentum. I also have a 12 kilogram block moving at 4 meters per second in the negative x direction, so that's negative momentum. And then the collision happens. That's the equal sign right there. And after the collision, I have a 3 kilogram block moving at 3 meters per second, and it's moving in the negative direction. I also have a 12 kilogram block, but I don't know whether it's going to the left or to the right. So I just make that a positive variable and solve for that variable, V final. If I get a positive number, it's moving to the right after the collision. If I get a negative number, it's moving to the left after the collision. So let's do the math. This is going to be 15. What's the units? Shout it out. The Franci, yes. That's the plural of Francis. When you get all the family together, they're Franci, okay? And so here I've got negative 48 Franci, and this is going to be negative 9 Franci plus 12 kilograms V final. Well, this is going to give me negative 33 Franci is equal to negative 9 Franci plus 12 kilograms V final. When I bring the negative 9 over, it becomes a positive 9. This becomes negative 24 Franci is equal to 12 kilogram V final. Well, that's going to give me V final is equal to negative 24 Franci over 12 kilograms. And that's going to be either minus 2 meters per second or 2 meters per second left. What it is not, what it will never be, is negative 2 meters per second left. Why? Because negative left is equal to the right. Okay, so this is just not only wrong, but sick and wrong. Sick and wrong. You can either write it like this or like that. Okay? Now, that's something you should be able to work out really quickly because there's going to be so many of those on the exam. And I can dance it different ways. Okay? For example, I could give you both of the final velocities, but only one of the initial velocities and ask you, what's the initial velocity of the blue block in order for this to happen? Okay. The other way that I could make this, I could dance this. Well, so the answer was 2 meters per second. But I could also, let me pause here and just make a point. if I look at the momentum of the red block, it changes from positive 15 Franci to negative 9. That is not conserved. That does not stay the same. If I look at the momentum of the blue block, it goes from negative 48 Franci to negative 24 Franci. That is not conserved. What is conserved is the total momentum of the system comprised of both blocks. When I add 15 to negative 48, I get negative 33. When I add negative 9 to negative 24, I get negative 33. That's what stays the same, the total momentum of the system, okay? Now, another way that I can dance this is to just say, what if they stick together? What if it's a total, a maximally inelastic collision? Okay, what would the final velocity be? And in that case, because they're moving together, they're stuck together, I can treat them as one ugly block of mass 15 kilograms. And so let's solve that. Whoever designed this room really made a mistake. I don't want to be critical, but really. Okay. So notice that before the collision, we got the same situation that we had before. That's the collision, that equal sign there. So I don't need to mess with the left-hand side. I just have to get rid of the right-hand side. Okay, and after the collision, if they're moving together, I would have 15 kilograms moving at some V final. That'd be 15 kilograms moving at some V final, and this would be 15 kilograms moving at some V final, and then this is going to be negative 33 Franci divided by 15 kilograms. And that's going to give me either negative 2.2 meters per second or 2.2 meters per second left. So the answer is 2.2 meters per second left. You see how the different ways that we can dance this problem, and you'll probably see all of those ways on the example. Questions? Okay, we're good. I just want to, this is belaboring the point, I know, but remember, I'm an old man. I've seen this show before. And over again, before the third exam, I get asked questions about, well, the three different flavors of collision. How do I distinguish between them? Okay, so this table, I hope, will settle that. For an elastic collision, mechanical energy is conserved. What about momentum? Conserved or not conserved? Conserved. For an inelastic collision, mechanical energy is not conserved, but momentum conserved, okay? For a maximally inelastic collision, again, mechanical energy is not conserved, but also we have the condition that they stick together. And momentum conserved. You cannot find a collision in the universe that does not conserve momentum. And when you think about it, that's because there's only one bucket. When we say that mechanical energy is not conserved, that's because mechanical energy is just those three types of energy that we have formulas for. If something warms up, that's heat energy that we haven't taken into account. If the frame of your Volvo gets messed up, that's deformation, energy of deformation that we don't have a formula for. And so by saying that mechanical energy is not conserved, It's because we put some of that energy into buckets that we don't have formulas for. But with momentum, there's just one bucket, mass times velocity. That's it. And so when we say that's conserved by Newton's third law, there's no wiggle room. There's no place to go. It either is or it isn't, and it is. Okay? Now, it appears sometimes that what I just told you just now is not true. Okay? There are going to be times in your life when you're going to see things that are going to suggest that Greg lied to me. Okay? For example, this piece of clay, if I throw it straight down, it stops. Well, that doesn't seem to conserve momentum, but it was a collision. Well, let's suppose that I drop that piece of clay from 5 meters. Okay, let's take that example. And let's say I started with 1 kilogram of clay. Well, I can figure out how fast it's going right before it hits the ground just by using energy. It started with potential energy, gravitational energy, mgh. M is 1, G is 10, H is 5. That's 50 joules. Okay, now, when I look at that 50 joules and turn it all into kinetic energy, that tells me that my final velocity right before it hits the ground is 10 meters per second down. Okay? And then it hits the ground and stops. Well, that's doesn't look like it was conserved. Well, first of all, let's ask ourselves, where did the energy go? I had 50 joules and now I don't. Where did that go? Well, if I look at this, it's now got a flat side that it didn't have before. We deformed it. If I really dropped it from 5 meters, this might be a little bit warmer when I picked it up. Some of it went into that thermal bucket. I've got all sorts of places where that energy could go. But if I look at the momentum, again, because that's a vector, I need a coordinate system. It had positive 10 meters per second. Positive 10 Franci. And then it had 0 Franci. If we believe that momentum is conserved in every collision, then we have to believe that 10 is equal to 0. Okay? Now, I hope that you cannot make that leap. That's just not true. That's just not true. And the reason it's not true is because we didn't do our part. Remember, I said it was a conditional promise that if you include everything in your system that collides, that hits, that bounces, that's the system that will conserve momentum. Well, this piece of clay hit the table, which is connected to the floor, which is connected to the building, which is connected to the earth. And we did not include the earth in our system. So let's go back and do that, okay? Let's include the earth. And so now, there's the 10 Franci for the clay. And then we have the mass of the earth and start in its rest frame, so that's 0. And then afterwards, the clay and the earth are stuck together. It's a maximally inelastic collision. So I have to combine their mass, and I solve for the final velocity. The earth sped up when I dropped that clay. Well, how much did it speed up? Well, if I plug in, there's my 10 Franci, there's the mass of the earth. Notice I didn't add 1 more kilogram. And then there's the V final. I solve for that and I get 2 times 10 to the minus 24 meters per second. Did you feel that? Did you feel that when I dropped the clay? No, you did not. Stop shaking your head. Yeah. Okay, that's just negligible. Forget about it. Okay. Now, what about the energy, the kinetic energy that we just gave to the earth? Well, that's 1/2 mv squared. The m is really big, 6 times 10 to the 24 kilograms. But that velocity that we gave the earth is squared. And so when I find the kinetic energy we gave to the earth, it's so tiny, it's negligible. That 50 joules that we started with, none of it went into speeding up the earth, practically speaking. It all went into the deformation and the heat. See if your neighbor follows what we just did there.
Yeah.
The message I'm trying to get across here is that never look at collision problems that involve the earth. You get numbers that are just too hard to make any sense of. And so you can talk about two Volvos, you can talk about a red block and a blue block, things like that, but never look at collisions between a car and the earth, or the car and a very sturdy wall that's connected to the earth. Those are never going to give you answers that you are going to be able to interpret. Okay. Let me give you some help with your tutorial homework, which is due tomorrow. Okay. At the end of that homework assignment, there are a couple of problems that involve Galilean transformations. And that sounds really scary, but it's not. A Galilean transformation is just another point of view, a different reference frame. Okay. And it's called a Galilean transformation because Galileo was the first to talk about this. But simply, it's just this. If we have a red Volkswagen moving at 30 miles an hour to the right and a blue pickup truck that's parked, Greg, standing on the sidewalk, is going to see just that. Okay? But if we look at things from the point of view of Jeff, who's on a big yellow dump truck that's also going 30 miles an hour to the right, what does everything look like from his perspective? Well, that parked blue pickup truck looks like it's coming towards Jeff at 30 miles an hour. But when Jeff looks out his side window, he sees that red Volkswagen. A little bit later, he looks out the side window. That red Volkswagen is still right there. And so what Jeff sees is that red Volkswagen is not moving in his reference frame, but the blue truck is coming towards him at 30 miles an hour. Okay? We call that a Galilean transformation, but it's just the same problem from a different point of view or a different reference frame. Now, what I want to point out is that Greg and Jeff don't agree on what the total momentum of this system is. Greg thinks that the total momentum of the system is small and to the right. Jeff thinks that the total momentum of the system is large and to the left. They do not agree on what that momentum is. But what they do agree on is if the red Volkswagen collides with the blue truck, the momentum after the system is going to be exactly the same as the momentum before the collision. After the collision will be the same as before the collision. They won't agree about what that is, but they will agree that it didn't change. See if your neighbor followed what I was saying there.
Yeah, I think
Now,
Same.
in the homework, you're actually given numbers like this. You've got this red block and you're given the mass of the blocks. This red block is going at 0.6 meters per second. The blue block's not moving. And if we look at this from the sidewalk frame, that's exactly what it looks like. Okay. But in the homework, we have Jeff on this big yellow block. And we're told that the yellow block has 5 times the mass of the red block. Is that important information? No, that's a red herring. That's just seeing if you'll use it. Okay? But if it's moving to the left at 0.2 meters per second, what does this whole thing look like from his point of view? Well, it looks like that blue block is moving away from him to the right at 0.2 meters per second. But what about the red block? Well, it's going to the right at 0.6. Jeff is going to the left at 0.2. In Jeff's reference frame, it looks like the red block is coming towards him at 0.8 meters per second. And I hope you have some gut level feeling for that driving down the freeway, okay? If we move the decimal place and say that's 60 miles an hour and that's 20 miles per hour, well, in Jeff's reference frame, that car is coming towards him at 80 miles an hour, okay? If he were parked, it would be 60 miles an hour, but he's going towards it at 20 miles an hour. They add. Okay, is that speaking to your soul? Okay, good. Questions? Yes, sir.
I still don't know why Jeff sees himself going that way.
What's that?
I still don't know why Jeff sees himself going. to the
Why he
right.
sees the blue one going that way? As Jeff moves this way, does the blue block get further away from him? If he's traveling at 20 miles an hour, the pickup truck doesn't stay right behind him. It's moving back in the past. Does that make sense? Okay. 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 Let's go back and talk about this problem of 14.4. Again, we had the boxcar traveling at 10 meters per second. The 4 boxcars that weren't moving, it collides and links. And what we found was that after it links, it moves off at 2 meters per second. Okay. That's where we've been. Well, what if instead of linking with the 4 cars, it bounces back at 1 meter per second? When it links, we got a final velocity of all the cars as 2 meters per second. If it bounces back at 1 meter per second, am I going to get a final velocity for these guys that's less than 2 meters per second, equal to 2 meters per second, or greater than 2 meters per second? So with your clicker, let's see what you believe there.
The original. Oh.
Okay, get it done. Last call. Whoa, okay. We are unsure. We are unsure. The answer is A, greater than, greater than. Now, this is one of the main ideas in that tutorial that you did last week. You remember there was one collision where the little block came in, hit the big block, and the little block stopped. And another collision where the little block came in, hit the big block, and bounced back. And you had a discussion between the students, and the one student said, in the first collision, the little block lost all of its momentum. And you can't lose more than all of your momentum. You can't lose more than everything. Well, folks, that's just not true if you have credit cards, okay? Or if momentum's a vector. Let me give you a personal example. Many years ago, in the 90s, there was a tech boom. Tech stocks were just taking off. And my wife was working for a doctor. She's a nurse, and she was working in a doctor's office. And he came in and he was just so happy. And he was a grumpy guy, but he was always so happy during those times. And he told my wife, he said, Sandra, I am making so much more money in the stock market right now than in my practice. You and Greg need to get in on this. It's just crazy. It's going crazy. And Sandra laughed and she said, we don't have any money to invest. Well, Satan has a way of tempting people. And right after she laughed at him, we each got a letter from Discover credit cards offering us, it came with a blank check for each of us, saying that we could write ourselves a check up to $20,000 and not pay it back for a year with no interest. And Sandra and I thought, whoa, free money. So we each wrote ourselves a check for $20,000. We invested in a single tech stock, Broadcom, that was just going crazy, that was just really, really taking off. 1 week before the crash, the great big dot-com crash, 1 week after we dumped that $40,000 into Broadcom, it was worth nothing. Did we lose everything? No, we lost more than everything. It wasn't our money. We weren't down to zero. We were $40,000 in the hole. Okay. And so the moral of that story is you never gamble with money that doesn't belong to you. And the corollary is you never gamble with money that does belong to you. Okay. So make sure that your neighbor understands that principle. Okay. With vectors, this is what it looks like. That one car came in with a certain momentum. It was 10 meters per second times whatever its mass was. Okay. Let's say that just to make the numbers work out, let's say the mass of that car was 1. Okay. That would give me an initial momentum of plus 10. Okay. And then after it links with those other 4 cars, it was going off at 2 meters per second. Again, if the mass was 1, that would be a momentum of 2. Well, what's the change there? What do I have to add to 10 to the right to get 2 to the right? 8 to the left, right? Now, what if that one car, the single car, bounces? It starts out with 10 to the right, but now it's got 1 to the left. And you remember when we're trying to find the difference, the change, we put them tail to tail. And we ask, what do we have to add to 10 to the right to get 1 to the left? Well, we've got to add 11 to the left. We've got to bring it all the way down to 0 and out the other way. Okay. Now, why do I care about the change in momentum for the one car? I want to know how fast the 4 cars are going. Well, that's because for the system, the change in momentum has to be 0 always. And so if the one car has a change of 8 to the left, the 4 cars have a change of 8 to the right. And in this case where it bounces, if the one car has a change of 11 to the left, the 4 cars have a change of 11 to the right. And so they have to be going faster in the case where the one car bounces. It has to be bigger than 2 meters per second. Yes, really.
Didn't the question ask if it was linked together though? Or did it ask if it bounced off?
The homework says they link together. I asked, what if it were a different question? What if instead it bounced? Would that give me an answer that was the same as what we had in the homework or bigger or smaller? Okay. Other questions? Yeah, in your homework it linked, but this would be a different problem.
It's
Okay. I just want to point out that I may have made things too black and white before when I said that every problem is either energy or momentum. As you've seen in your homework, a lot of problems have different parts to them, an A, a B, a C, and a D. And one of those may be an energy problem and one may be a momentum problem. For example, in this problem, we have a kid on a skateboard. The wheels on the skateboard are really, really good so that we don't have to worry about friction, okay? And this kid catches a 5 kilogram, that's a pretty heavy football, going at 10 meters per second. And he catches it. And so that's going to be a collision. And I know that it's going to be a maximally inelastic collision because they move together. And so if I conserve momentum, I can figure out how fast he's going right after he catches that ball. And then if I were to ask, how high does he go up this ramp before he stops and turns around and comes back down? Well, that's going to be an energy conservation if those wheels are really, really good. And so this problem, I would have to break up into two parts, one during the collision to find out how fast he's going at the bottom of the hill. And then second, I conserve energy to find out how high he goes up the hill. Does that make sense? It's not just always cut and dry energy or momentum. Sometimes you have to break it up into parts. So I have for your enjoyment 2 old exam problems that involve energy and momentum. I need my helpers. Where are my helpers here? There we go. And another helper. Helpers over here. Thank you. That's another helper. Thank you. Sir. Okay, there's,
let's see, there's like.
thank you. You have one extra there? Oh. Okay. It's like passing the sacrament. It's always just that one person at the end of the, oh, what are you gonna do? I didn't get this section here. Okay, raise your hand if you still need one.
No, do you guys need one?
Yeah. He's direct.
How slow.
Picture.
Okay. We've got a hand that pushes on this block. The block has a mass of 3 kilograms. And it gets it up to some speed. And then the block hits this rough patch with a coefficient of kinetic friction of 0.3. And that slows it down. And after it passes over that rough patch, it's moving at 8 meters per second. And the first part of this problem, part A, asks us to find that distance of the rough patch. How far does it have friction? And so I do my decision tree. Is this a collision? Well, there will be a collision in part B, but it hasn't happened yet. So no. Is time involved? No, distance is involved. So this is an energy problem. So I start every energy problem here. Energy initial is equal to energy final, except when it's not. And it's not when there's external Verk done. Well, there's two types of Verk done. The hand is doing positive Verk, putting energy in, and then the friction is doing negative Verk, taking energy out. Now, if I look at the initial energy before the hand starts pushing, well, okay, so I'll take the initial to be at the start. And the final would be right before collision. At each of those times, I ask the same three questions. Is anything with mass moving at the start? No, not until the hand pushes. Is anything up off the floor? No. Are any springs stretched or compressed? No. So I've got a big fat zero here, okay? And then I've got Verk done by the hand. The hand's pushing with 75 newtons for a distance of 2 meters. And then I've got the friction doing negative Verk. And then right before I have the collision, I ask the same three questions again. Is anything with mass moving? Yes. So I have 1/2 times the mass of 3 kilograms times the speed of 8 meters per second squared. Remember that square, that's where a lot of people make their mistake. They write it, but they don't put it in their calculator, okay? Now, I then ask the other question, is anything up off the floor? No. Any spring, stretch, or compressed? No. So that's going to be my final energy. Okay, so I start with 0. I add 150 joules. And then, well, what's that friction force? Well, anytime I'm looking for a force, I draw a free body diagram. I've got the earth on the block, that's 30 newtons. It's on a level surface, so the normal force by the track on the block, or we'll call it the floor on the block, would also be 30 newtons. And so the friction force, because it's kinetic friction, would be mu sub k times the normal force. That's going to be 0.3 times 30 newtons, or 9 newtons. So this is going to be minus 9 newtons times delta x. 8 squared is 64. Half of 3 is 1.5. 1.5 times 64 is 96 joules. Okay? Well, that's just algebra. And if I solve that for delta x, what I get is delta x is equal to 6 meters. See if your neighbor could have solved that problem if it were on your exam.
I need to do work.
Okay. Questions on that part? Yes, sir.
You saying there's 2 and done?
With that?
There's two different types.
Yes.
Done.
Yes. First, the hand does positive Verk, and then the friction does negative Verk. There's no inherent limit that I can only have one piece of work. Yeah. But I'm glad you asked that question, because when this was on an exam, that's where a lot of people broke down. They just, how do I deal with 2 different works? What do I put in? And some people wanted to make some kind of funny average, and that's not the way it works. Okay. Now, in part B, we have the collision. And so that's conservation of momentum. And we're told that after the collision, block B, the big block of 7 kilograms, is moving to the right with 4 meters per second. So let's find out what the little block is doing after the collision. We conserve momentum. Because it's a vector, we need a coordinate system. Right before the collision, we had the 3 kilogram block moving at 8 meters per second. And we had the 7 kilogram block not moving at all. So I just wasted ink. Okay. And then we have the collision. We have the 3 kilogram block. I don't know how fast it's going or what direction it's going. So I just make that a positive variable. If I solve for that variable and get a negative answer, I find that the little block bounced back to the left. But I do know that the 7 kilogram block was moving at 4 meters per second after the collision in the positive direction. So this gives me 24 Franci plus 0 is equal to 3 kilograms V final plus 28 Franci. If I subtract the 28 from both sides, I get negative 4 Franci is equal to 3 kilogram V final. And that gives me V final is equal to negative 4 Franci over 3 kilograms is equal to negative 4/3 meters per second. Or I could say 4/3 meters per second left. Either of those would be correct. Okay. Now, the total kinetic energy of the 2-block system right before I've got 1/2 times 3 kilograms times 8 meters per second squared plus 1/2 times 7 kilograms times 0 meters per second squared. Well, that's 0. And that's just 96 joules. If I look after the collision, I get 1/2 times 3 kilograms times 4/3 meters per second squared. Notice I didn't put a minus sign there. I'm going to square it. I just need the speed. The speed is always a positive number. And then I've got 1/2 times 7 kilograms times 4 meters per second squared. And this is going to be equal to 2.67 joules plus 56 joules. And that's going to give me 58.67 joules. If I were to ask you what flavor of collision is this, you would need 2 pieces of information. You would say, well, my initial kinetic energy is not equal to my final kinetic energy. So that means it's not an elastic collision. And you would also have to say they don't stick together. So it's not a maximally inelastic collision. So it has to be inelastic. Now, how do I know that they didn't stick together? Well, one's going to the left and one's going to the right. They're not stuck together. Okay. If they're stuck together, I'm going to get the same final velocity for both of them. Check that your neighbor's on the bus, please. Do a buddy check.
Yes.
Are there questions about that problem? Yes, sir. I'm sorry?
No, it's not elastic.
Yes. If it were elastic, the final kinetic energy would also be 96 joules. Yep. Yeah, because we lost mechanical energy, it can't be elastic. Okay? Well, turn that page over and let's look at the other problem. This one, we have the hand pushing with 900 newtons, but we don't know how far it pushes. But we know that when it's done pushing, it's going 15 meters per second. And then it collides with block B, and then block B moves over this rough patch. So talk to your neighbor about how you're gonna solve this while I erase the board.
No.
Yeah, I started the wrong one too.
I should have used it. Same thing. When that happens.
It's worked.
No, we did.
This is him.
Okay, we only have a few minutes left. And parts A through E are very, very similar to the other problem. But part F is the part that's very different that we didn't see before. And that is that big block, the 8-kilogram block, it is sliding right after the collision at a speed of 8 meters per second. And we want to know for how many seconds will it slide on that rough section before it stops. And so if we look at that last part, this is part F. We do that decision tree. Is this a collision? No, the collision's already happened. And now block B is just sliding across a rough part of the floor. And is time involved? Yes, it is. So we go right here, P initial plus force delta T is equal to P final. If I call to the right, the positive direction, then I have P initial is 8 kilograms times 8 meters per second, and it's positive. The friction force is to the left, so it's negative. And the friction force I would get from a free body diagram, the weight is going to be 80 newtons. The normal is going to be 80 newtons. This is going to be kinetic friction, so it's going to be mu sub k times the normal force. The mu sub k is 0.7 times 80 is going to give me 56 newtons. Okay, and so that's going to be 56 newtons times delta T. It brings it to a halt. And when I solve that for delta T, what I get is delta T is going to be 64 Franci over 56 newtons. And that's going to be 1 point something. We've run out of time, people. Thank you for your attention today, and I hope that this has helped to clear some things up.